Hello, my name is Michelle Tomczyk, and I'm in Jeremy Levy's group at the University of Pittsburgh. Today I'll be discussing a two-dimensional to one-dimensional crossover that we see in nanowires at the interface of lanthanum aluminate and strontium titanate. So quantum transport in two-dimensional systems has been extensively studied, from ultra-clean semiconductor quantum wells exhibiting large quantum oscillations, which indicate ballistic transport on length scales well over a micron, to high-mobility graphene with quantized Hall resistance and even fractional quantum Hall effect. And another two-dimensional system of interest is the interface between lanthanum aluminate and strontium titanate, where a two-dimensional electron system, two-dimensional electron liquid forms when the lanthanum aluminate is above a critical thickness of 4 or more unit cells. Additional confinement can be achieved by gating 2D heterostructures or growing semiconductor nanowires in carbon nanotubes. These these devices extend the scope of quantum transport into the one-dimensional regime. In the LAO-STO system, one-dimensional structures have also been achieved to make use of the unique advantages of one-dimensional physics. But why are we interested in this complex oxide system? In fact, this two-dimensional interface boasts a very wide range of intrinsic physical phenomena. The 2DEG is reversibly and hysteretically tunable through the metal-insulator transition. It has gate-tunable spin-orbit coupling, as well as natively hosts superconductivity, which can be modulated by gating. And it even shows evidence of magnetic phases. So basically the system contains a large collection or anthology of phenomena in solid-state physics. Now it turns out that there's evidence that the interface system may not be as two-dimensional as it seems. Using squid magnetometry, I'll see a very non-uniform current density. These resolution-limited channels carry a significantly larger current density than the bulk two-dimensional background. The channels are aligned with the crystal axes and correlate to the formation of these ferroelastic domain walls. So perhaps mobility is being enhanced by the strain at the domain walls. Whatever the mechanism, it seems that the transport of intrinsically one-dimensional nature may be contributing even to the transport, the two-dimensional transport at the interface. So it's important to characterize the one-dimensional transport in the system. And in fact, we've been doing that. Since about 2008, our group has pioneered a unique lithography technique where a conducting AFM tip is used to create customizable, reconfigurable, narrow conducting channels at this interface. So our collaborators grow the lanthanum aluminate layer just below the critical thickness so that the interface is insulating but highly tunable. Using a conducting AFM tip and applying a positive voltage, as we drag the AFM tip across the surface of the LAO, it leaves a path of positively charged protons, which act as sort of a local top gate, tuning the interface below them through the metal insulator transition. This process is also reversible by applying a negative bias to the tip. We can remove the protons, restoring the insulating state. In this way, we can create nanoconstrictions and tunneling barriers in these interface nanowires, which are around 2 to 20 nanometers in width. Some devices created using this lithography technique include single electron transistors, Fabry-Perot cavities, and quantum point contacts. Devices such as these, along with the nanowires themselves, allow us to probe the electronic phenomena at the interface, to observe quantum interference and quantized conductance plateaus that evolve in magnetic field. We also see enhanced mobility extending to room temperature, a strongly correlated phase in which electrons pair far outside of the superconducting state, and gate-tunable electron-electron interactions. So the question is, so now can we bridge this gap between the two-dimensional interface and our one-dimensional nanowires? To study the crossover between 2D and 1D, we created a series of Hallbar devices of various widths. The green lines here indicate where the conducting channels are being created at the interface. Assuming a Gaussian potential profile for a typical nanowire, 10 nanometers width, a series of densely spaced lines gives an overall profile with a much larger width. These devices are cooled to 2 Kelvin for transport measurements. And in each device, we have current flowing through the 2 sections of wire of different widths. And these voltage leads here permit more sensitive 4-terminal measurements. Typically, the narrow wire section was a single nanowire, around 10 nanometers wide, while the wide section was varied from 20 to 200 nanometers, and all sections are 5 micrometers long. A backgate voltage can be applied to the back of the STO substrate, allowing us to electrostatically control the wire properties. So here I will mostly concentrate on data from a single device made of a 10 nanometer nanowire and a 200 nanometer wide wire. So this data is typical of devices in the width series. So first we look at the backgate dependence of the conductance, and we see that the nanowire saturates around 2e squared over h, while the wide wire has a much higher conductance. At low backgates, the wide wire seems to come down and saturate around 1e squared over h. But in order to better compare the wires, we want to scale the conductance by the dimensionality of the wires. Look at the conductivity. So if the interface hosts uniformly connecting channels, we would expect the conductivities of the 2 wires to be similar. So here, plotted on the same scale, we see the striking result that not only does the conductance not scale with the width of the wire, in fact, the greatest conductivity achieved in the wide wire only reaches the lowest conductivity in the narrow channel. So this suggests a significant difference between the transport properties of wider 2-dimensional channels and these narrow 1-dimensional nanowires. So perhaps one explanation of what's happening in our wide wires is that as we tune to these negative backgates, we could be depleting the low conductivity 2-dimensional bulk, leaving these 1-dimensional gutter-like channels along the edge of the wire. In order to study this further, we now apply a perpendicular magnetic field to the sample. So we do magnetoresistance measurements, and we see that at high positive side backgates, we see a significant difference between the magnetoresistance in the 2 wires. The wide wire takes on this very parabolic shape over the whole field range, while the parabolic shape is suppressed in the nanowire, which instead shows this weak antilocalization at low fields. At low backgates, however, we see a surprising result where the magnetoresistance of this 200 nanometer wire now becomes nearly identical to the magnetoresistance of the nanowire. To quantify this transition, we fit the high field magnetoresistance to a second-order polynomial and plotted the b-squared coefficients. So here we can see that as the backgate is decreased, the 200 nanometer wire loses the parabolic shape. That parabolic shape is suppressed as we're able, indicating that we are able to, or suggesting that we're able to electrostatically tune this wire, this wide wire, through a dimensional crossover into the quasi-one-dimensional regime. Controlling this dimensional crossover, this indicates that we can control the dimensional crossover not only by creating wires of varying widths, but by electrostatically tuning wide wires into a depleted 1-dimensional regime. And so this electrostatically tunable dimensionality can allow us to probe the dimensional dependence of various interface properties, such as mobility, spin-orbit coupling, magnetism, strongly correlated phases, as well as, for example, superconductivity and critical current density, the dimensional dependence of which will be discussed tomorrow in session V30. These are exciting questions that we hope to continue to address with future experiments. Thank you.